Good afternoon. That's almost the end of our course, penultimate lecture. Yeah, that's how it's called. I mean, next time will be the last one. And of course, we were not able to cover all the topics that were planned. This is also normal. I mean, this is also part of the plan. So let's start. We will try to cover as many things as we possibly can. Last time was about quantum Hall effect, and it was a sigma model with the topological term and the two-parameter scaling that describes how transition between quantum Hall plateaus happen. So today we start with the same topic about quantum Hall effect, but now from a different perspective. This time it will be about quantum Hall edges. Quantum Hall edges. And this is much easier actually than it's an alternative description of the quantum Hall effect, but in some sense it's easier than the one that we had last time. But also it gives the same results. So in a sense it's alternative explanation, which some of you might find more better to understand. And yeah, so what do we know about quantum Hall system? Just imagine this is our sample. It's a rectangle. This is a two-dimensional electron gas, and there is some magnetic field that penetrates it. And there are electrons in this plane. So what these electrons do, they go in this circular orbits, cyclotron orbits, and they are quantized. So each of these orbits should have some integer number of wavelengths along it. That's why we have Landau levels, so only certain energies are allowed. But other than these circular orbits, there is something that happens at the edge of the sample. An electron is trying to do the same circular thing, but only half of the circle fits here, so the electron bumps at the edge and goes like this and can go around the corner and continue along this edge and so on. So this is called a skipping orbit. It's like the same cyclotron trajectory, but near the edge of the sample. And we can also draw a similar picture. This is the same x coordinate, left edge, right edge, but now vertically we will have energy. And somewhere in the bulk, here in the middle of the sample, our energies are quantized. There are Landau levels, like this. There are certain values of energy that are allowed. And if you do this, it's quite a simple quantum mechanical problem to find Landau levels, but in a geometry which has walls here and here, you will see that this energy actually is a constant inside, but starts changing when you approach this wall, and namely these levels will bend up near the edge. And the same thing they do on the other side. They bend like this. So now if we fill this spectrum with electrons up to a certain level, which is the Fermi energy or chemical potential, these states that are below, they are completely filled. So we have this picture corresponds to the filling factor 2. We have 2 Landau levels filled, but we also have this bending, which means there are some states exactly at the Fermi level, but these states exist only close to the edges, and these are exactly the skipping orbits, the ones that propagate along the boundary. They have this energy at the Fermi level. And they propagate, so if we have 2 Landau levels filled in the bulk, we also have 2 distinct edge modes. And this is the exact correspondence. The number of filled levels in the bulk is the same as the number of edge modes. All these edge modes propagate in the same direction. In this picture, they propagate like this, counterclockwise. So for example, if we fill 2 of them, there will be two channels, 2 different types of states that propagate, and actually they look exactly like Landau levels. I mean, this part is the same as in the bulk, but they just skip like that. So we have skipping orbits, or this is like in this semi-classical picture, or more scientifically they are called edge modes or edge states. It's the same term, edge states. And now when we add disorder to the system, what happens is that all states in the bulk here are localized. They are immobile. They can still circle around, but they stay in the same place. This circle is pinned by impurities. But the edge modes never localize. They do not localize. No matter how much disorder you add, it's not possible to localize these states for a simple reason, because they propagate only in one direction. So both modes here propagate counterclockwise. If you add impurities, the only thing impurity can do, it can scatter between different states. So it can scatter from this state to this state and back, but no matter how your electron jumps between these 2 states, it continues to propagate in the same direction. That's why this current due to these modes cannot be stopped by disorder. And this is an explanation how quantum Hall effect avoids localization, how these edge modes avoid localization. And when you measure the Hall response, you pass the current from one side to the other. Actually, this current flows along the edge. This lower edge gets more populated than the upper edge because you have this excess current. And it means that you have some voltage between upper and lower edge because this one is more populated, so its chemical potential gets higher than on the other edge, and that's the voltage. So you can simply explain that Hall conductivity, Hall conductance, the ratio between voltage and current, is a quantized quantity, and the quantization, this coefficient, is an integer number which is equal to the number of these edge modes. This is the way how we describe the state inside the quantum Hall plateau. It's not a transition. Our chemical potential is between Landau levels. Everything in the bulk is localized, and the Hall conductance is an integer number. Then, if we change this chemical potential, we can eventually pass through the next Landau level, and at this point, the number of edge modes changes. It was 2, it becomes 3, and at this very point where this number changes, there is no full localization in the bulk. So the states in the bulk, they are not localized. That's why we can take a new state and put it at the edge. It's only possible if there is no localization in the bulk. So we cannot describe really the critical point, but in this language, the transition between 2 states with different filling factors, but at least we see that there should be some critical state there. So if this picture is clear, we can now do some calculations, not just pictures. Is this clear? Are there any questions to this thing? Okay, so as usual, for a disordered system, we would like to have a description in terms of the sigma model, as usual, because this is the proper description for any disordered system, which captures the relevant degrees of freedom. So we will have something which I call edge sigma model. Edge, sorry, sigma is written like this. Edge sigma model. So imagine we would like to describe only these edge states, not the bulk of the system. Bulk is localized, bulk is boring, nothing happens there. We are at some quantum Hall plateau, so sigma xy is integer. Sigma xy is integer. But we still have something happening at the edge. So these edge modes, they're still not localized, they can propagate, and we can describe them with a sigma model. And this will be one-dimensional sigma model. Yeah? Our edge is a one-dimensional object, and we can write something like a Hamiltonian for these edge modes. How shall we do this? Let's first do the Hamiltonian as a plot. Hamiltonian is energy as a function of momentum. And in 1D we have only one component of momentum, so this is the momentum that goes along the edge in our 1D direction. And we have this number of edge modes, like 2 here, and they have velocities only in one direction. So it should look something like this. 1 and 2. Just the straight line, and the slope means slope corresponds to velocity. Energy is linear in momentum. It's like we had this written before, psi equals v times p. Velocity times momentum. So this picture corresponds to that particular case, but I will study a more general case. Let's say we have 3 modes propagating to the right, and at the same time we have some modes propagating in the opposite direction. So now this picture does not correspond to the quantum Hall above. It's a more general one. So in general, I will assume that there are some integer number n r of modes propagating to the right, and some other integer number n left modes propagating to the left. I can of course assume that all modes are propagating to the right, but then there is no point of doing any theory, because whatever you do, they still propagate to the right. If we have modes that propagate in both directions, we can do some meaningful scattering. We can scatter from here to there, and there is a chance to localize at least something. But if the two numbers, right and left, are not equal, we will not localize all of them. We still will end up with some number that is not localized. So I will assume that the number of right and left modes is different. This can be actually done experimentally. There are experiments like this when you take two samples with quantum Hall effect, but with different magnetic field. You apply stronger magnetic field here and weaker magnetic field here, and then you make a junction between them. So one edge is attached to another edge. It's like this. We have two samples, and we have, for example, 3 edge modes going inside this sample, B1, and here we have some other magnetic field B2, which makes only 2 edge modes, and they propagate like this. So here in the middle, if you look only along this edge, we have 3 modes in one direction and 2 modes in the opposite direction. And then if we really make a junction between them, there is a possibility to be scattered. So electron can propagate here, then jump due to impurity and propagate in the opposite direction. Okay, so this is my model, and psi that I have here now, this velocity, will be actually an operator. It's a matrix. It's not just a number. And this matrix V will be like this. It will be a number, V, just velocity, meters per second. And then it's a matrix with a number 1, which is repeated n right times, and then number -1 that is repeated n left times. So it's a diagonal matrix with plus and minus 1 on the diagonal. So we have 3 modes, or n right modes with velocity v, and n left modes with velocity minus v that propagate in the opposite direction. And for simplicity, I assume that all velocities have the same magnitude. So these lines, they have all the same slope. Actually, this is not important. You can also assume that the slopes are different and the result will not depend on this. But it's just easier to work this way. So my goal is to start with this Hamiltonian, to add random potential to it, and to derive a sigma model in one dimension. And, well, let's first ask ourselves what is the density of states in such a system? Density of states. Nu. Density of states is the coefficient in this identity. Nu d psi should be the same as dp divided by 2 pi. Yeah? We usually integrate over all states either in momentum representation, and this is one-dimensional, so p is just a number, or as an integral over psi with the coefficient nu. And here, if I do dp by 2 pi, I should multiply it with the total number of modes, and right plus and left. To count all states, I have dp over 2 pi states on each branch, so the total number should be multiplied by the number of branches here. And nu d psi, on the other hand, is d psi. Psi is v times p, is just nu times v times dp. So if I compare this to that, I can cancel out dp. Nu is total number of modes divided by 2 pi v. Actually, this is correct for any one-dimensional system. Each channel, each line on this plot has its own contribution to the density of states, and the larger is the velocity, the smaller is the density of states. Large velocity means more steep line, which means less states per unit momentum. Okay, so this is nu. Another question, what is the diffusion constant? Diffusion constant, we all know it's v squared times tau divided by d, but this is one-dimensional, so divided by 1. And since we know these two things, we know what sigma is. Sigma is e squared nu d. This is nu, this is d. This is nu, this is d. If I multiply them, v cancels out once, and I have n right plus n left divided by 2 pi and multiplied by the mean free path, L. Just a reminder, L is v times tau. So this is the conductivity. It has a dimension. It has a dimension of length. So if I divide it by the length of the sample, this will be a dimensionless conductance in inverse ohms. So this is the conductivity. Now, how do we derive sigma model? Exactly the same way as we did it before, and I will not repeat this whole procedure. I will go directly to this stage. So sigma model has the action S of Q. This is last but one step in the derivation. It was step like 6, I believe. And it says the following: minus trace of logarithm of this operator, epsilon minus xi plus I q over 2 tau. I put omega equals 0 for simplicity. There's no omega. It's after we integrated out fermions, but before we do gradient expansion. So sigma model, this is not yet the sigma model. If we do gradient expansion of this object, we will get the sigma model. But now this xi here, it's an operator. Xi is this operator. It's V times P, and V is a matrix. So it's an operator that has a size of the number of channels at least. And this trace also includes trace over all channels. Before we did this calculation, before it was trace in real space, it was like trace for the operators in a very general form. So now xi is the operator that has this particular form. We have to trace this. So this is what will happen. I will have minus n right trace logarithm. Let me also neglect epsilon. Epsilon is the Fermi energy counted from, no, is the energy counted from the Fermi energy. So let's stay just at the Fermi energy. Let's set epsilon to 0. Minus xi means, well, actually, you know what? Actually, I can keep epsilon there. It doesn't matter. Epsilon plus I v d by dx plus iq over 2 tau. This is what happens in the channels that propagate to the right. Xi is just 1 times v times p, and p is minus I d by dx, and minus xi means plus here. And then there is another portion which is number of left propagating channels with a trace of logarithm, but this time it's epsilon minus iv d by dx plus iq over 2 tau. So I just have written explicitly this trace over channels. I have a number of contributions for right channels and another number for left channels, and xi has opposite sign for them, but otherwise it's the same, and Q matrix is also the same. Q matrix is a single matrix for all channels. It does not discriminate between them. Is it clear? Yeah. I already thrown it away because I know that Q squared is 1 at the saddle point, so this term is just a number. It's a constant. Yes. I will actually do gradient expansion at the saddle point anyway. If you like, we can add it, but it will not change. So it will determine the saddle point, but it will not participate in gradient expansion. Yeah, there is also a term with trace Q squared, of course. So our goal is to do the gradient expansion of this thing. So we do it as usual, as we did before. Trace log. Let's take this first one. Trace of logarithm of epsilon plus IV d by dx plus I over 2 tau, and the Q matrix is T inverse lambda T. See, now I'm in the saddle point. I already replaced Q matrix with something that squares to 1, so I don't need this other term. So what we do, we multiply this whole thing with T inverse from one side and with T from the other side. And we have trace log epsilon plus IV d by dx plus I lambda over 2 tau. This happens if t is a constant, it commutes with d by dx, so it just cancels. But if it's not a constant, it does not commute. Then it provides some correction to this term, plus what? Plus t derivative of t inverse. Derivative should act on t inverse. It provides a minus sign. Minus I. Ooh. Oops. What just happened? Where is my text? Yeah. Minus I V yeah, dt by dx times t inverse. We already did this calculation, so I do not explain literally every step. So this is a small correction to here due to the gradients of t. And gradient expansion means expand in this term. And this first one is like zero order approximation. And I will...
The result should be the same, right?
The same than what?
As it was when we described sigma model the first time.
Almost the same, you will see. So it's some constant times trace logarithm 1 plus minus, sorry. It doesn't erase with a hand anymore. Minus, I have minus I, minus IV, and then epsilon minus, let me put back the momentum representation, minus Vp plus I lambda over 2 tau inverse times dt by dx times t inverse. So it's a logarithm. I took the logarithm of this first part away, and then what is left is 1 plus this thing multiplied by the inverse. It's my green function, actually. It's what was called g last time. And since it's an expansion, it's a gradient expansion, I now expand in this whole term. So 1 is the main term, and this is a small correction. I expand the logarithm near the point 1. So the first term of this expansion is minus IV, just the trace of this, trace of epsilon minus Vp plus I lambda over 2 tau inverse times dt by dx t inverse. Plus the next term, plus the quadratic term. So what we did last time, we expanded up to quadratic term, and we actually neglected this term because it was 0. What I will do now, I will now neglect the quadratic term because we already know what it provides. We already did this calculation. But this first term will not actually cancel. So this is the crucial point. This trace of the green function times something. Actually, this trace here provided the integral, the green function at coincident points. It was the integral of the green function over all momenta. And this is the green function computed at all momenta. So before I tell you what it is, I just want you to remind you the self-consistent Born approximation equation.
I'm sorry, does T depend on momentum?
T depends on x point. And this is a derivative. But it's a slow function. It depends, but slowly. And this thing decays on the scale of mean free path. Just a reminder, 1 over 2 pi nu tau, this is a impurity line, it's this diagram, times the integral nu d psi of energy minus psi plus or minus I over 2 tau, retarded or advanced function. This thing equals the self-energy, which itself is minus or plus for retarded and advanced I over 2 tau. This is the self-consistency equation, and I already substituted here the correct solution. 1 over 2 tau is the solution. So what I have here in this trace, this thing inverse, is actually this integral, exactly this integral, and instead of plus 1 or minus 1, I have matrix lambda, which is plus or minus 1. It's just a diagonal matrix. So this integral actually equals, I can easily find what it does. It's 2 tau cancels, it's I pi nu minus I pi nu lambda. So for plus, if I have plus 1 inside, I have minus. If I have minus inside, I have plus, so it's minus lambda. It's the opposite to what stays inside lambda, and I pi nu is just the rest, this pi nu here and this I from here.
And the real part of this integral
Is discarded. You can say it's 0 because it's an odd function of psi.
Yeah, but the real part is diverges and it's multiplied over.
It diverges, but it is 0 at the same time because this is an odd function of psi. So if I really have this linear spectrum, really literally linear, and I have some cutoff of my integral which is symmetric up and down, it will be 0.
So it's not clear why this term does not have impact with the T.
Okay, we can
Depends on cutoff.
we can put it differently. This term, if it imagine it's not 0, then it will be the same for retarded and advanced. It does not depend on whether I put plus or minus here. So this imaginary part has lambda, but the real part, if it's not 0, has just the unit matrix. And then it's like a total derivative. Okay, so this was a reminder. This is not part of our calculation. It's just a reminder. And actually, we can say the same if we did how Misha proposed. If we added a q squared term and do a proper saddle point, we will see that this is also the saddle point equation. So that this integral equals to this. It's equivalent to self-consistent Born. We already discussed this. So the only thing I want to find from here, I have minus I, minus, minus. Now nu, I have nu here, and nu is what? What is nu? nu is actually 1 over 2 pi v, because I don't have summation of channels of this integral. It's just the momentum integral. Number of channels was taken out already earlier. So this is just the real space integral, just dp. So nu is, so what I have here is minus pi v, and then nu is 1 over 2 pi v. This is quite boring, right? And then I have trace t inverse lambda dt by dx. So it's minus 1/2 of this trace. And of course I have the quadratic term, which I do not specify here. Okay. So if I now do this thing, I have computed just one trace of this type, but actually I have n right minus n right such traces here, and minus n left similar traces here, but with the opposite sign. So the true action, is integral over x, one-dimensional action, trace, then inside the trace I have quadratic term, which we usually write like d gradient q squared. It also has pi nu over 4, I will put it inside, pi nu d over 4 dq by dx squared. This is our quadratic term. It comes from this parts that I discarded. I just know the answer, so I put it here. But we also have the linear term, because number of right and left modes is different. So number of right, once again, minus number of right times this. It means plus number of right modes minus number of left modes divided by 2, trace t inverse lambda dt by dx. So this is my sigma model. It looks exactly like it was before, with an extra term. And this extra term appears only because I have an imbalance. Number of right and left modes is different. In what we did before, when we derived the sigma model in a usual situation, there was a symmetry. The average velocity was 0. Number of states with velocity to the right, or in any direction, was the same as in the opposite direction. So this term cancels in what we did before. That's why we expanded to the next order. But in this particular case, when we have one-dimensional system with imbalance, it will not cancel, so this term remains here. No, that's not my intention. This term remains, and the first one is actually a standard one. I can also put here nu times d. We just calculated what it is. It's number of right plus number of left divided by 8 times mean free path. This prefactor here. Yeah, so it has at least the correct dimension x, and L is length squared, and we have x squared in the derivative. That's nice. And this thing is dimensionless. We have x here, d by dx here, and it's a dimensionless number. So I wonder why nobody asks any questions, because this is outrageous. This type of action is outrageous. Nobody has any
Why do you think so?
problem with it, because it's not written in terms of Q matrix. It literally violates all the principles that were proposed earlier. The action, look, we had trace log something, we had the Q matrix inside, it was just literally Q matrix. we do gradient expansion, and we have something that is not a function, not explicitly a function of Q matrix. Which means this, for example, this thing violates gauge symmetry. Yeah? When you do gauge transformation, matrix T changes, but matrix Q doesn't. So the action should not change, but it will because it's written in terms of T. This is outrageous. Another outrageous thing is that I have a trace of a trace. This should not happen. I have a trace outside. So this thing, this term here, has a name. Such terms do appear in field theories sometimes. They're very specific. They explicitly violate gauge symmetry. Nevertheless, gauge symmetry is actually there with some proper, well, if you do gauge transformation in a proper way. So such term has a name. It's called WZW-term. WZW-term. Or just WZW-term. Still no questions? Probably my explanation wasn't good enough. WZW-term is, well,
The same Witten as Q.
yes, it's the same Eugen-Witten. And it's also the same term that we have seen last time.
Actually, the first time when we did gradient expansion, the fact that action can be written in terms of Q matrix also was like a miracle. So now it's not.
Look, it might have looked like a miracle, but actually there is a reason for this, and the reason is gauge symmetry. So if this miracle doesn't happen, it means you did something wrong. And actually, this is an exception. We did everything correctly, and still it's not written in terms of Q, but another reminder from the last lecture. Let me remind you what was with the Pruiskin term. Pruiskin term looked like this. It was the same quantum Hall thing. Sigma xy divided by 4. Two-dimensional integral of trace of Q, nabla xq, nabla yq. And we did this calculation last time, and we found that it equals to minus sigma xy over 2, the integral along the boundary of the sample, circulation of a certain vector ds, trace exactly this thing, T inverse, lambda nabla T. This is the same term. This is the same.
Okay.
Yep.
So the point was like why the not confused because of second term doesn't consist in Q. It was your
The concern is that the last term is not written in terms of Q.
and it should be a problem.
Yes.
Um,
So I see, since you don't know that it should be a problem, it's not a problem, right? Once again, there is a gauge symmetry. Look, we had just a few steps before, we had the action, this one, which has Q inside. Q and Q. There's no T matrix, right? Only Q. Then we say Q is actually T inverse lambda T, this combination, and we do some expansion and get whatever result. Now, gauge symmetry means that I can change the matrix T. I can do this thing. I can change matrix T to matrix K times T such that K commutes with lambda. And if I do this change, the Q matrix, which is T inverse lambda T, changes to remain just the same. It doesn't change. This is a gauge symmetry. I can change matrix T such that Q remains the same. Since the action was written in terms of Q, it should be gauge invariant. If I change T like this, it should not change the action. Now, I scroll this whole thing back, and we see that the action will change if I do the gauge transformation. It should be written only in terms of Q, not in terms of T, in order to be gauge invariant. For example, the Prussian term is gauge invariant. It is written in terms of Q. But this Prussian term equals, we did this last time, this is a two-dimensional integral in the sample. It equals to the circulation, to the integral along the boundary of some object that does violate gauge symmetry, which is not a function of Q. And we discussed that time that if we do gauge transformation, then what will happen is that this term will change, but we will just add a total derivative to it. Derivative of the logarithm of the determinant of that K matrix. And it will not change any equations of motion, and actually if sigma xy is integer, it will not change even nothing quantum. So this is a reminder. This, actually, if you like, we have just derived the sigma model together with the Prussian term. Last time I told you Prussian term was derived by Prussian. Nobody can repeat this, which is correct. Nobody can. What we did now, we derived the sigma model for the edge, not for the bulk, for the edge. And we see that at the edge, we have this term, which looks very strange, but actually, it's the same as if we write not this term on the edge, but this term in the bulk. And we can compare the coefficient. This is sigma xy over 2, and this is n right minus n left over 2. So sigma xy is exactly this integer number, n right minus n left. Exactly what it should be on a quantum Hall plateau. Imagine now, let's go back a few steps. Imagine now we have only right propagating channels and nothing propagates to the left, nothing. N left is 0. And n right is our sigma xy. Is the number of edge modes, is the integer number of edge modes, and it's exactly the same as here. So what we did, we derived the sigma model with the Prussian term, not in a general case, but only on the quantum Hall plateau when sigma xy is integer. Prussian did it for any value of sigma xy, even when it's not integer. That thing is very complicated. We just did the simple calculation when in the bulk everything is localized. There is no life happening there. All modes live only on the edge, but they still remember that there was some sigma xy in the bulk, and that sigma xy was integer and it was equal to the number of edge modes. So we actually derived the Prussian term in this particular case, but using a very indirect approach, going to edge theory rather than considering the bulk theory. Yep.
You just said that this action works at the plateau, right?
Yes.
And where we use this?
Because it's one-dimensional.
No, where we use that sigma xy integer, only where we compare results, or
Because we do it on the edge. When we are at the plateau, everything is localized in the bulk, and electrons can propagate only along the edge, and we can, in principle, derive an edge theory. When they are not localized in the bulk, when they can go from the edge there and back. There is no point in, there is no such notion as the one-dimensional Hamiltonian for these edges because we have only a two-dimensional Hamiltonian. Okay, so conclusion. Conclusion. I forgot it. I have to read. What was the conclusion? There's no conclusion. Okay, so there are two different things. There is a theta term, the one that Pruskin did. This is a theta term. Now I will write a general statement. Theta term in d dimensions. In our case, d equals 2, but can be actually anything. Theta term in d dimensions is literally the same as the WZW-term term in d minus 1 dimension. In 2 dimensions, we have a Pruskin term. This is a theta term, and it equals the one-dimensional term in dimension d minus 1, and there it is called WZW term. In a one-dimensional theory, such term is called WZW. So they are literally the same thing. I mean, it's the same expression, but they have absolutely different properties. Just let's compare. Theta term has any prefactor. Sigma xy can be any number. We had this flow diagram where sigma xy was on one axis, sigma xx was on the other, so we can start from any point in this plane, sigma xy takes any value, then it flows to some integer number, but it can start with any value. So in the sigma model we can have, in the two-dimensional sigma model, we can have any value of sigma xy. So the prefactor of this theta term can be any number, has any prefactor, but it takes, the term takes quantized values. We also discussed this. We discussed that it's a topological charge. It's the degree of mapping from the real space to sigma model space. So this term takes discrete integer values, but they are multiplied with any prefactor. This is about theta term. Now, WZW term, one-dimensional theory, WZW term, which is just here above the edge, it has integer prefactor. It can have only integer prefactor, which is number of channels, and right minus and left is an integer number. Integer prefactor. But actually, if you compute this integral along some particular, with some particular Q matrix, with some particular value of t, it can take any value. Takes any value. It's just the opposite. Pruskin term, any prefactor, takes only integer values. WZW term here should have integer value because we should be at the plateau. We can reduce the theory from 2 dimensions to 1 dimension only if we localize everything in the bulk. And this happens only when sigma xy is integer. That's why integer prefactor. But then, if we look at this one-dimensional theory that lives only on the edge and we integrate along the edge this object, it will take any values, any real values. I mean, it has continuous spectrum.
So it's like 1 over L perturbation to this quantized values.
No, it's not a perturbation. Why you call it a perturbation? I will right now.
We can use the for the case when everything is localized and the results should be the same,
Yeah,
but it takes only quantized values.
because if sigma xy is not quantized, it means that not everything is localized in the bulk. And the two-dimensional theory does not reduce to one-dimensional.
But the integrals are
Integrals are equal.
the same.
Yeah,
How the right one can take any
because it has the, because in this case, I will explain right now actually. That was my point to illustrate this. So, example. I'm not sure, I hope that you know this example to some extent, but if not, I will try to explain. Example. Example has a name, and we could have a separate lecture about this topic, but we don't. Example is called berry phase. How many of you know what berry phase is? Okay, everybody knows, so we can skip it and go for it. Example. So imagine you have a unit vector n. N is a unit vector. It lives on the sphere, and it depends on what? On one variable, say on x, or on time, doesn't matter. We have n which varies in time or in space. It's a unit vector, yeah, n squared equals 1. It lives on the sphere. This is the sphere, the unit sphere. So as x changes along, or time changes, this n has some trajectory in the sphere. Goes along a trajectory, and we will consider only closed trajectories, meaning that it should necessarily return to the original point. Actually, it's usually the function of time, and periodicity in time is a very natural condition. So, berry phase is a particular term that can be added to the action, which is the solid angle covered by this trajectory. Berry phase equals solid angle covered by this trajectory. Berry phase is the WZW-term in this theory. Yeah.
What's the question?
Hmm?
What you try to show?
I am trying to illustrate how it happens that theta term is quantized and WZW-term is not. So this is a WZW-Witten term. It's just a particular example of this WZW term. In one dimension, actually it's exactly that one that we have in the sigma model. It's exactly, if you take one replica, your Q matrix lives on a literal sphere, and this berry phase is literally that term.
So both of them quantized.
Both of whom?
WZW-term and that
No,
term.
only theta term is quantized, but not WZW. It's written, look, takes any value. It's not quantized because the solid angle takes any value. You can have a solid angle which covers only 1/10 of a sphere, or half of the sphere, or the full sphere, any value. Right? This is the only thing you really need. You need the trajectory to be closed. You cannot calculate berry phase for a trajectory that has a beginning and end, because you don't know how to encircle this solid angle.
Sorry, what is the theta term in this?
It's a WZW-Witten term. There is no theta term here yet.
Okay.
Only WZW-Witten term. Now, there is a way, well, actually it can be written explicitly, I don't remember how, like something like integral dx sine squared theta over 2 times d phi by dx, I believe. Theta and phi are coordinates, these spherical coordinates in the sphere. So this is just the solid angle. Then consider a different question. Now, imagine you have a unit vector which depends now, which lives in 2 dimensions, depends on x and y. And now we can write something that is called theta term for 2-dimensional theory. Again, it's exactly that theta term we have in the sigma model. In the case of one replica, it's literally living on a sphere, so it will be literally this. Theta term looks like this. Theta term is an integral dx dy n dot dn by dx cross dn by dy. This is a cross product and then scalar product, with some prefect that I do not remember. Now, if you calculate this integral for this n, it will count the degree of the map n, maps from xy to a sphere. This mapping has a degree. This degree is an integer number. But it's an integer number provided that your 2-dimensional n lives also in a sphere. So certain boundary conditions, somewhere at infinity in this xy plane, n takes the same value on the whole boundary. So it maps xy is like a sphere, it maps sphere to the sphere, and we count the degree of the map.
Okay, so you mean that they're equal in terms that they have the same expressions, but they are applicable for different situations?
Yeah.
So this is the reason why
So degree of the map actually is the solid angle divided by 4 pi. Yeah. 4 pi means you covered once, 8 pi means you have covered it twice, and so on. So actually this term and that term are exactly the same integral. Just this integral, well, it's a 2-dimensional, but it can be reduced to a dimensional along the boundary of that type. The difference why they produce different results are in the boundary conditions. In 2 dimensions, we say our Q matrix must be the same at infinity, or our n vector must be the same at infinity, which means we map the whole sphere to the whole sphere, and the degree of the map should be an integer number. That's theta term. Now, this theta term can be written as the integral along the boundary of this, of this thing, but theta and phi, they should change along the boundary such that the vector n is constant. Now, question, how does it happen? How n can be a constant, but theta and phi change? Any ideas? It happens when n points, say, down, theta equals pi over 2, but phi can rotate. When the Earth rotates, North Pole stays the same. I mean, North Pole doesn't have a longitude. You can change the longitude and stay at the same point. And that's exactly how it happens. I mean, in order to have some non-trivial coverage with a degree not equal to 0, you inevitably will have this matrix T not a constant at the edge. So Q matrix will be a constant, but T will not. And it will count this winding around the South Pole, and it will give you the degree. And it will be done with this term. Now, in this case, when we have a one-dimensional theory, nobody told us that Q should be a constant. Yeah? Q can change along this. So it's like now we're considering a system of a quantum Hall effect, which are fixed at the plateau, sigma xy is integer, everything is localized, but we do not demand that the Q matrix is constant at the boundary. Now Q matrix lives on the boundary. It's a one-dimensional boundary theory, and Q matrix is some object which can change. That's why the Zumina term is not quantized. And actually it counts this fractional degree of the map. It's a map not from the full sphere, but from a rectangle, something with a boundary, mapped on the sphere, so there is a boundary in this map, it doesn't require it to cover the sphere completely. This degree of coverage can be a fractional number. And the solid angle is not quantized.
So the real metals term exist only for really large sample, when we can suppose that geometrics
Yeah.
in the bulk is almost
So it's the same expression as an integral of the same integrand, but we use it in two very different contexts. Either as a term in a two-dimensional theory, and we impose on this two-dimensional theory certain boundary conditions, namely we say it's a very large sample and Q matrix is fixed at infinity. And then we have a theta term. Another condition is we do not fix Q matrix at the boundary. It still can change the way it likes, but we fix the value of sigma xy of the prefactor such that nothing happens in the bulk, everything is localized, and that's the WZW term. So we quantize the prefactor such that we can now use the only for this particular integer values of the prefactor, this WZW term actually is gauge invariant. Remember, we have a problem with gauge invariance. We can do transformation. This transformation t we can replace by k times t. Let me show this. We can replace, we have to wait a little bit. Yeah, we can replace t by k times t such that k commutes with lambda. This is our gauge transformation. WZW term has a trace of t inverse lambda dt by dx. It transforms into itself trace t inverse lambda dt by dx plus k inverse lambda dk by dx. If we do gauge transformation, this term changes. Now, k commutes with lambda, which means it has two blocks, retarded and advanced. And this trace, we can drop lambda from here, is the difference. We did it last time, actually. So it's like a derivative of the logarithm of kr minus logarithm of ka. And if we do it on a closed trajectory, k should return to the same value where it started. This logarithm integrated, the derivative integrated, takes an integer value. I mean, not this one, this takes any value, but the addition due to gauge transformation can take only integer value. And it must be multiplied by the integer prefactor such that any gauge transformation always adds 2 pi I to the action and can be actually dropped. So gauge invariance of the WZW term is restored. It manifestly breaks gauge symmetry, but the gauge symmetry will be restored provided the prefactor is integer, and only in this case. For theta term, it's already gauge invariant. It's written in terms of Q. No problem. Prefactor can be anything. Yeah. Are there any? Probably I should write it in some more precise way. Maybe not. I don't know. Yeah, actually, let's try this. There are a few subtle points to this thing. Let's just check. So, WZW term, the way we had it here, had a prefactor. Had a it's broken once again. it had a prefactor n right minus n left over 2. It's the integral dx, and the prefactor was, let me write, m over 2. M is the imbalance. M is number of right minus number of left. It's an integer number which corresponds to sigma xy. So here I will have the same. I will have an integral over dx m over 2. Right? Does everybody understand? If I put kt here and t inverse k inverse here, I can act with my derivative either on t or on k, and then I have either this term or that term. That should be easy. So let's consider, so this term is the same as it was originally. When we did this gauge transformation, this is the addition, this is what is added. So this term, which was added with a prefactor, is m over 2 trace k inverse lambda dk dx integral over x d by dx a logarithm of determinant of kr minus logarithm of determinant of ka. And k, since it commutes with lambda, is this block diagonal matrix with retarded and advanced block. And now, Andrei, specifically, you asked this question last time. And I told you there is an additional restriction that determinant of k must be equal to 1. And the determinant of kr is the inverse of the determinant of ka. And I can now explain why, because we did this calculation. Actually, it's a bit tricky, and I have to scroll it back and it will freeze again. So I will say in words. There was this part when we have trace, log, and this operator with the T matrix, that we did the gradient expansion. And in order to do this gradient expansion, we did a rotation by T and by T inverse from two sides. Actually, this rotation corresponds to a change of variables in terms of the original fermionic integral. And this change of variables has a Jacobian. And in order for this Jacobian to be unity, we should apply a condition that determinant of T, of the matrix that rotates these fields, is unity. And since T is replaced by KT, to maintain this identity, we should demand that determinant of K is also unity.
Well, but when we write the action in terms of Q matrix, there is no any fermionic variables anymore.
This is correct.
And we can use any T matrix which satisfy the condition on Q.
Okay, so I will scroll it again with the hope that it will work. It's not about Q, actually, it's about this specific operator. It's a subtle point, but yeah, this operator, this one. Trace log something in terms of Q. The problem is with the Hamiltonian here, not with the Q matrix. The Hamiltonian is a linear function of momentum, which means the spectrum is not bounded. We have eigenvalues infinitely large and eigenvalues infinitely large and negative. Yeah, this is just a linear dispersion. It goes from minus to plus infinity. This particular case is very well known as an example of what is called chiral anomaly. When you have we compute a determinant of an operator that has unbounded spectrum. This is a tricky thing. Formally it diverges, this determinant, I mean. And you have to impose a certain cutoff for the spectrum in order to make it finite. This is well studied in the context of high energy physics under the name of chiral anomaly. Because they have very similar thing. It's like the Dirac-Hamiltonian. And Dirac-Hamiltonian is also linear in momentum. It's gamma times p. So whenever you do a determinant of a Dirac operator, you always have this problem. And it's also related to gauge symmetry. So when we do this T inverse, this rotation, it's like a gauge transformation, but for the fermionic fields. And it's, again, in this context in high energy physics, gauge transformation of the fermionic fields that correspond to a Dirac fermion generates some anomalous contribution, which means that in order to maintain the real gauge symmetry of the problem, you should require that this rotation matrix has determinant 1. It's not a proof, it's just an explanation where it comes from.
Like when I have non-unit determinant, I will have some problems with the regularization.
Yeah. Well, you still can regularize it, but then this regularization should
Cancel.
no, it should obey gauge symmetry. So you should regularize it such that the gauge symmetry is preserved. You cannot just say there is a maximum p and minimum p. This is wrong because then gauge transformation shifts p and your boundaries are shifting as well, your cutoffs. Okay, we don't need to go into all these details. I'm just saying that when we had the symmetric case and right equals and left, this problem does not arise because whatever anomalous contribution coming from this expansion is cancelled by the other one. But when n right and n left are different, these anomalous contributions from these two determinants, they do not cancel. So in principle, before we had the equal number of right and left, so yes, determinant was formally divergent, but whatever happens there at large energies cancels because we have the same number for right and left. And now it doesn't cancel, so to ensure that they do not appear at all, we just need a very, very, very little additional condition that T should have determinant 1. It doesn't change the signal model in the end. The signal model is just the same, but this is a subtle point. And yeah, whenever determinant of T is 1, means determinant of K is also should be 1, and determinant of K retarded and K advanced should multiply to give 1. So that's these two determinants are actually the sum of them, the sum of this logarithm is 0. These two logarithms sum up to 0, so I can as well write m times the integral of derivative of logarithm of a single determinant of only k retarded. That is the same. Twice this logarithm. And this integral is 2 pi I times integer number. This integral is 2 pi I times some integer number because k, we are going on a closed trajectory. K should return to the original value. And this logarithm is the phase, so it can rotate only by an integer number of 2 pi I. And this number should be also integer. Then the product is also integer. And what we do, we add, when we do a gauge transformation, we always add to the action only an integer multiple of 2 pi I. So in the exponent, it has no physical consequence. Okay? So now everybody else can wake up. We already passed this very interesting point. So, once again, theta term and Vesuviana term looks exactly the same, but exist in adjacent dimensions. Theta term in dimension d and Vesuviana term in dimension d minus 1. But one of them is the integral of a total derivative, and the other one is what happens with that one if you do the partial integration and reduce the integral to the boundary. but they have slightly different properties. One of them, theta term, is explicitly gauge symmetric. WZW term is gauge symmetric only if it has an integer prefactor, and it should be proven it's not explicitly gauge symmetric. And vice versa, theta term takes only integer values, it counts the degree of covering. WZW term also counts the degree of covering, but it's a fractional covering, it's not the full, it doesn't cover the full space, so it can take any values. Okay, great. So if there is no questions up to this point, are there no questions? If there is no questions, then we move on to the next topic. We are finally done with the quantum Hall effect. And we start a new topic.
Sorry, and what about the term with T? Also, it's
Which term?
just separate K and T. Calculate the input of K.
Yeah, actually, this is a gauge transformation. So this term remains itself plus something. This something appeared due to gauge transformation. So the new topic is very different from the previous one, and the new topic is quantum spin Hall effect. Spin minus Hall. So quantum Hall effect was the first example of a topological effect in the theory of localization. It is first in this course, and also it is first historically. I mean, in physics, this was the first thing observed. Quantum spin Hall effect is the second historical thing, which was observed only around 20 years ago. And still some people do not believe that it's real. So it's some variation. It's a variation. It's a time reversal version of usual Hall effect, of usual quantum Hall effect. What happens if we take usual quantum Hall effect that we just discussed and force time reversal symmetry on it? First of all, time reversal symmetry cannot coexist with magnetic field. It's ridiculous, right? So what people invented is the following thing. Just imagine this is our sample. It's still rectangular, we just look at it from a side. There is some magnetic field, and there are some edge modes that propagate along the boundary. This is a quantum Hall effect. Imagine now I take a second sample, which is exactly the same, another two-dimensional electron gas, but there I will apply the opposite magnetic field. And it will have an edge mode that propagates in the opposite direction. So this system is almost time reversal symmetric. It has this thing and that thing. If I reverse time, I interchange them. Yeah, I like flip the system. B up becomes B down, and vice versa. So this system actually is not time reversal symmetric. It's just a combination of two quantum Hall effects. And to make it really time reversal symmetric, they also say let's add spin orbit coupling such that this is actually the same system, but for electrons with spin up, they feel this up magnetic field. So in this H mode is like for electrons with spin up, and for electrons with spin down, effectively we have the opposite magnetic field. So it's possible actually, if we have a system, it's not a real magnetic field now, it's a very strong spin orbit coupling. Spin orbit coupling looks like this. electron has an orbit, it has some trajectory, it moves. And when it moves along its trajectory, it feels some effective magnetic field, so its spin tries to align according to momentum. So it's like we have momentum-dependent magnetic field, which acts on the spin. And this momentum-dependent magnetic field is such that if you move in this direction, you feel the field up, and if you move in the opposite, you feel the opposite. So, to be more specific, time reversal version of quantum Hall effect is actually some system of symplectic symmetry with strong spin-orbit coupling with the Hamiltonian that is, which has time reversal symmetry like this, sigma y, yeah. Time reversal symmetry that squares to -1 and has a form of very strong spin-orbit coupling. I will not write the Hamiltonian explicitly, but you can do this. I mean, this picture is almost like writing the Hamiltonian. So, what we will do for this case, we will again do the following. We will consider only the edge theory. So bulk is somehow localized. There are no states there. We have edge modes that propagate only along the edge. But now we have these modes with spin and modes with spin up propagate in one direction, modes with spin down propagate in the opposite direction. Edge theory. Edge theory is written in terms of the one-dimensional Hamiltonian, 1D Hamiltonian, that looks like this. Psi equals velocity operator times momentum. It's one-dimensional. And the velocity operator is a number v times a matrix 1 minus 1. We have channels propagating in one direction and channels propagating in opposite direction. Actually, it's n of them, and -1 is also n of them. And this Hamiltonian actually has time reversal symmetry, provided this number is the same. The number of left and right is the same, and this plus -1 is actually spin. This is my Hamiltonian. It's V times sigma z times p. This is the Hamiltonian. And this is the sigma z matrix. You can check this, obeys this symmetry. So it's exactly the same Hamiltonian we just considered for edge modes. But in that case, we had different number of right and left, and the difference between them produced a WZW term. Now in this case, we have the same number of right and left because there is a time reversal symmetry. We are not allowed to have imbalance because time reversal makes electrons move in the opposite direction. But, so the number is still the same. And if we consider this left-right thing as a spin, we even have a time reversal symmetry of the symplectic type. And still, this is a non-trivial system because this number n can be either even or odd. And it was suggested that if the number is odd, or if it's just one, if we have just one mode here and the second mode there, they still cannot be localized. They cannot be localized because the backscattering, any impurity cannot scatter this state to the opposite state because it should also flip the spin. And if this impurity obeys time reversal symmetry, it cannot flip the spin. I mean, if it's a potential impurity, if it's just potential, it doesn't act on the spin, so it will not be backscattered, so it will not be localized. Turns out that this is all correct, and even a more general thing is correct. I mean, if you have this time reversal symmetry and an odd number of channels, two things, you can prove that this edge will not be fully localized. Only it will be almost localized, but not fully. So we will prove it right now. This is easy. This is a calculation we just did already for the unitary class. So we do a sigma model for this exactly Hamiltonian. But now this will be a sigma model of symplectic class, not of the unitary class. Can anybody remind me what is this sigma model of symplectic class? What's the difference between unitary and symplectic? Sigma model. Sigma model class A2. This is symplectic A2. U matrix belongs to a certain symmetric space.
Yeah, to unitary over symplectic.
Sorry?
As is S, yeah.
S is unitary over symplectic, and this is O over twice O. It's O 4n actually, divided by twice ON. Oh, 2n, yeah, sure, 2n. So how can we write such a Q matrix? Easily. Q matrix equals T inverse lambda T. But now matrix T belongs to the orthogonal group and not to unitary. So there is a restriction. Well, actually, yeah, okay. T matrix, T inverse is the same as T transpose, orthogonal group. And Q matrix just equals Q matrix transposed. Yeah, this is symmetric matrix. It's T transpose lambda T. So symplectic class is the same as unitary with the additional constraint on the Q matrix, that it should be a symmetric matrix. It should square to 1, be the same as in unitary. Everything is the same, but on top of this, it should be symmetric. How do we derive this sigma model? Actually, we never did. That's why I'm not allowed to ask you how to derive the sigma model, but I can tell you that we can do all the same steps, going from the Hamiltonian, doing this, that, disorder, decoupling, and then we arrive at this expression, S of Q equals, guess what? Minus trace logarithm, and then epsilon plus IV ddx plus IQ over 2 tau. And this thing should be repeated n over 2 times. N is the number of channels. We have n right and n left. Yeah? This n. This, sorry, it's different n. This n here. The number of channels. Minus the same number, n over 2 trace logarithm, epsilon minus IV ddx plus IQ over 2 tau. So there are only two distinctions between this case and unitary class. Distinction 1, there is an extra factor 1/2 here in front of the logarithm that wasn't there. Yeah, there we had just n right and left. Here we have n right and n left are the same, but the prefactor is twice smaller. This is one distinction. The second distinction, Q matrix actually is twice larger because it's 4n instead of 2n, but it's twice larger, but it has an extra constraint. And actually it means that there are exactly twice more variables inside this Q matrix compared to the unitary class. So when you expand matrix with a factor 2, it gets 4 times more entries. But then you apply an additional constraint which kills half of them, and this Q matrix in the orthogonal class is exactly twice larger. I mean, the spaces, the dimension of this space is exactly twice larger than for unitary class. And it should be so because symplectic class contains all the same diffusons plus the same amount of couperons that were missing in the unitary class. So we have twice more soft modes. Our Q matrix has twice more variables. And there is also one other interesting thing. I will do it right on the board because it's fine. So Q matrix equals Q transpose. They are equal. Q equals Q transpose. Let's take this second logarithm and transpose it. Transpose the operator that stays here. What will happen if we transpose this operator? Any suggestions? Yes, not because I is antisymmetric, but because d by dx is antisymmetric. Yeah, right. So transposition will not change Q matrix because it's symmetric, will not change this because it's number. It will change this sign, so this logarithm will be just exactly the same as this one. They are actually equal. So, since I can erase this second term, and I can erase this 1/2. That's it. It's just twice the same thing, so it's just minus n times this logarithm.
This is the same as in unitary class.
No, well, looks similar. And we already did expansion of this logarithm, right? We did it for unitary class just recently, just a few minutes earlier. So I can expand this thing again as we did there, and I get the, after gradient expansion, so gradient expansion, I already know the answer. Gradient expansion. S of Q equals, let me read my notes, integral over x, trace. First there should be this term gradient Q squared that we always have, n times L over 8 dq by dx squared. It's the same quadratic term that we had in the unitary class, and this prefactor n times L is actually nu times d, because nu is proportional to the number of channels and d is proportional to the mean free path, and all the rest cancels out. And also plus to this will be plus n over 2 t inverse lambda dt by dx. We have already seen this before, right? We had n right minus n left. So now we have everything in a single term. There is nothing to minus. It's just that. And now, Andrei, this was your personal homework to prove that this is 0. From the last lecture, you asked why we do not add Prussian term in other classes. The answer was we can, but they are 0. And this is an example. So this is almost like a Prussian term. Remember, it's just No, it's easy. It's very easy. Let me show you. T inverse actually is T transposed because it's symplectic class. So what you do, it's a trace of this object. You can just take a transpose of this object. Trace will not change. Yeah? When you transpose a matrix, trace doesn't change. If you transpose this, you will have dt by dx here and T transpose there. Then you do integration by parts. You move this derivative from the first term back to the last. And you discover that after transposition, this thing changes sign. Because this partial integration goes with a minus sign. So it should be 0. And actually, we will do it right now. So this, for some yet unknown reason, I will call this part here. I will call this part here as top, yes, like an index top, as top equals n over 2 integral over x trace T transpose lambda dt by dx equals n over 2. I just take a transposition of this thing, integral dx, trace dt transposed by dx lambda t, right? When you transpose, you flip the order of matrices. And then I will apply partial integration, so I will take this derivative in x and shift it to the other term. So this is minus n over 2 integral dx trace, what would it be? T transpose lambda dt by dx. So it just flipped sign. This term equals to minus itself. That's why it is always 0. Now, if you start with a two-dimensional case, two-dimensional model, and you add a Prussian term, two-dimensional model of symplectic class, and you add a Prussian term, this Prussian term equals to this integral along the boundary. And this integral along the boundary is 0. So the original Prussian term is also 0. There's no need to calculate it. Actually, you can prove it 0 without going to boundary. You can just transpose the product of 3 Q matrices and then do partial integration in the two-dimensional integrals. You will also see it changes sign. So it's perfect. We have proven that this is nothing. We can just drop this term. It's just the usual one-dimensional sigma model. It doesn't care of any topology. End of the story. And actually this is wrong, because somebody told us that if we have only one channel, if n equals 1, we have only one channel, in this quantum spin Hall effect, it should not be localized. There should be some reason why it cannot be localized. And when we do the sigma model, we don't see any difference. N equals 1, 2, 3, nobody cares. So if it localizes for some n, it should localize for all n. So there is some contradiction here. Where is the caveat in this argument? Who can guess? It's quite tricky. This is a quite tricky question.
Well, we suppose that we have two spin states with opposite directions.
Yes.
But if we have just one.
No. We have two. One means one pair of states. One left and one right. Yeah, actually, how shall I formulate this? this is wrong. T, oops, sorry. This is the caveat. T inverse is not equal to T transposed. Q is a symmetric matrix. Q equals Q transposed. But this thing doesn't. This thing is correct. T inverse equals T transposed only in a certain gauge. But we can do a gauge transformation which will violate this identity, which will not change the Q matrix because it's a gauge transformation. So actually the correct form is the following. Well, for most applications, for like 99% of applications, you can say that T inverse is T transposed in this class. But for this particular case, we should assume that T inverse indeed equals T transposed up to multiplication by K. So when we transpose the Q matrix, T changes to T transposed, but we can add any gauge transformation, so Q matrix will not change, T will change. So this is the, so let me put it this way. If the Q matrix equals T inverse lambda T, and on top of this we demand that Q is a symmetric matrix, to fulfill this condition, we don't have to say that T is orthogonal. We should say that T transposed and T inverse are just related by simple rotation. That, as usual, whenever you see letter K, it means this letter commutes with lambda. We can check. Q transposed equals, let's transpose this thing. T transposed lambda T inverse transposed, right? Oh, sorry. Yeah, no, that's correct. Now, T, oh my god, T inverse transposed according to this is TK T inverse K inverse transposed times lambda and T, sorry, I got lost. T transposed is T inverse K inverse times lambda, and this thing is transpose of T inverse. Ah, no, this is wrong. This is wrong. This is, sorry, this is wrong. It's T transposed times K from the other side. Like this. So Q transposed is T transposed lambda T inverse transposed. T transposed is T inverse K inverse. T transposed is T inverse K inverse times lambda T inverse transposed times K inverse times what? Just KT, yeah. K. Which one?
T minus 1 is equal to T transpose K. You just transpose that expression.
I transpose this expression, T inverse transposed equals K transpose T. K transpose T. This becomes funnier and funnier. Okay, so probably there should be some extra condition on k. So k commutes with lambda, and then it should also cancel here.
K commutes with lambda because anyway it's
But
block
yeah,
diagonal, so
yeah.
But
it's
each
not
block,
trivial why k minus 1 cancels with the kt.
I just said there should be an additional constraint on k such that they cancel.
K minus 1. So you just said that k is orthogonal. So t is orthogonal.
No. If t is orthogonal, k is orthogonal. And then everything works. Two orthogonal matrices are related by orthogonal k. That's fine. K should be symmetric. Well, if k is symmetric, then no problem.
I mean, k minus 1 times kt should be.
Okay?
Yeah.
I agree. K is symmetric. Whatever you say, K is symmetric. Yeah. So it's not orthogonal. It's a different thing. So what I'm trying to say is that, look, in principle, we can have orthogonal T matrix, and then we just prove that this term is 0. But we also have a Q matrix. Our Q matrix, when we go around our sample has no, I mean, it has boundary, but this boundary has no end. It's a closed loop. When we go around our sample, Q matrix comes back to the same value where it started, and we should parameterize it with a T matrix such that T matrix also comes back to the same value. And it might happen that Q matrix comes to the same value, but T matrix does not. It comes to the same value only up to this multiplication. Only, sorry, that's tough. Let's just do the calculation. It's an easy calculation. So I would like to fix this. So this calculation was wrong. That happened here. What I want to do instead, I want to do the correct calculation. And the correct will be like this. This topological action equals n over 2 integral trace, now t inverse lambda dt by dx. Inverse and transpose is not the same. Then we do transposition here, because trace doesn't change under transposition, and have integral dx trace dt transpose by dx lambda t inverse transpose. Then we apply this identity. T transposed and T inverse are not the same, but related by a k rotation. So T transpose is T inverse k inverse. So we have n over 2 integral dx trace. Instead of T transpose, we will have T inverse, d T inverse by dx lambda t plus, actually I don't know, k inverse lambda dk by dx. This is what I have written in my notes, and I am pretty sure that it's correct. So it's the same story as we had with the gauge transformation. Each t has matrix k inside, and if derivative does not act on this k, k cancels and we have this term. And if derivative acts on k, then t cancels and we have the second term. And finally, for this term, we apply integration by parts. And this is minus the original term. So what I'm trying to say is that this calculation was wrong because T inverse is not the same as T transpose. So if we have this k here and we apply this thing, it doesn't just flip sign, it flips sign, but there is an addition here with this k. And we can make a conclusion. We make a conclusion that this topological term equals n integral over x. This is integral over x trace k inverse lambda dk by dx. Yeah, I just take this. It's with a minus. I put it here. Twice this term equals. Oh, sorry. It should be n over 4, right? N over 4. Okay, so that's it. I never showed you this matrix K. I just told you that it should in principle exist. And this matrix K actually, it's now the same drill. I mean, it commutes with lambda, so it breaks into two blocks. In each block we have just derivative of the logarithm of determinant. So this integral is an integral of the total derivative. It goes along the closed path, so it takes some 2 pi I whatever number. And actually, if you do all the calculation carefully, you can show that this thing is I pi n. N is this n times an integer. This integer depends on k, on what particular matrix k we have. So this winding of the phase takes only integer values, and all the rest is this. So we conclude that there are exactly two cases. If the number n is even, if we have an even number of channels, this is 2 pi I, and then the topological term indeed is identically 0, and we don't need to consider it. But if n is an odd number, then this topological term takes exactly two values, only two possibilities. It equals either 0 or I pi. Well, actually it can be any integer number times I pi, but if it's an even number, it doesn't matter, and if it's odd number, I can reduce it to just 1. So we are done. This is the last equation of today. This object has a name. All objects have a name. This one also has a name, and it's called a theta term. Theta term, I just remind you, is something that takes only discrete values, has 0 variance. I mean, if you try to do small variations of Q, it's fully topological. So this thing is Z2 theta term. It's a theta term it counts it. How to say it? It takes discrete values depending on the homotopy class of your Q matrix. I mean, so any continuous deformations of Q do not change it, and Z2 means that it takes only two values. Before we had it counted the degree of covering, so it took infinitely many values. I mean, all integer numbers. This one takes only two values. So it happens because pi1 of O for n by O to n, O to n, it just happens so that this homotopy group equals Z2. We will discuss it next time. Don't pay attention. I'm just saying it has all the same properties as the Prussian term, as the usual theta term. It takes discrete values. The only distinction is that in this case there are only two distinct values and not any integer number. And as a consequence, the prefactor of this theta term is also quantized. I mean, in the Prussian case, sigma xy could be any number. The prefactor here is n is the number of channels. It's also integer. And unlike Prussian term, so we had a theta term which is the same as WZW term, but one dimension less. This theta term is Z2 theta term, and it doesn't have corresponding WZW term in a smaller dimension. It's just, it exists only in the dimension where it exists. So that's all for today, and next time I will say many more words about this Z2 theta term. If anybody is going to come next time.